Welcome to chapter 10 with the title Mechanical and Sound Wave. So under this chapter, we have 5 subtopics. The first one, 10.1, Properties of Wave. 10.2, Superposition of Wave. 10.3, Sound Intensity. 10.4, Application of Standing Wave. And the last one, 10.5, Droplet Effect. So this chapter requires 2.5 credit hours for the face-to-face SLT for the lecture mode. Here is the learning outcomes. At the end of this topic, students should be able to: the first one, 10.1 Properties of Wave, define wavelength and wave number, discuss particle vibrational velocity and the wave propagation velocity, discuss the graph of displacement time yt and displacement distance yx. For 10.2, superposition of wave, state the principle of superposition of wave for the constructive and destructive interference. 10.3, sound intensity, define sound intensity and discuss the dependence of intensity on amplitude and distance from the point source by using graphical illustrations. 10.4, application of standing wave, solve problems related to the fundamental and overtone frequency for stress string and air columns for both open and closed end. And the last one, 10.5, droplet effect, state droplet effect for sound wave. So basically, we have two types of wave. The first one, mechanical wave, and the second one is electromagnetic wave. So, for mechanical wave, the wave must have a medium or matter to travel through. For example, we have water wave, sound wave, wave on a string or rope, wave in a spring, etc. For the electromagnetic wave, the wave do not require a medium to travel because they can travel through a vacuum at a speed of 3 × 10⁸ meters per second. For example, we have light, radio wave, microwave, infrared, and X-ray. So next, we have the definition of mechanical wave. So the mechanical wave is defined as disturbance that travels through particles of the medium to transfer the energy. The particles oscillate around their equilibrium position but do not travel. A continuous repetitive disturbance gives rise to a continuous propagation of energy that we call as the wave motion. So let's say we have a string or rope here. So we shake the rope. The vibration of the rope will produce a movement of energy. So meaning the energy is being transferred from one point to another point. So based on the transfer of energy, we have two types of mechanical wave. The first one, progressive wave or traveling wave. The second one is standing wave or stationary wave. So for 10.1 properties of wave, we have the definition of the progressive wave. The progressive wave is defined as a wave that propagated continuously outward from a source of disturbance. So we have some terms used to describe the wave. The first one, amplitude, with the symbol capital A, is defined as the maximum displacement from the equilibrium position to the crest or trough of the wave motion. So this is a value of amplitude. This is also the amplitude. Basically, it's the maximum vertical displacement. Next, we have particle displacement with the symbol small y. So defined as a vertical displacement of the particle from its equilibrium position. So actually this is the equilibrium position, and any value of the vertical displacement is called the particle displacement with the symbol small y. Next, we have wave displacement, x, is the distance of particle from the source of disturbance. So here is a source of disturbance. So any value from the source of disturbance is called the wave displacement. Next, we have frequency with the symbol small f, the number of complete waveforms that pass a given point in 1 second. For the period, we have the symbol capital T. It's defined as a time for one complete wavefront or a wavelength to pass by a given point. So the formula given here is T equal to 1 over F. Next, we have the wavelength with the symbol lambda. It's defined as the first one, distance between two successive crests or troughs, or distance between any two successive identical points on the wave. For the wave number with the symbol small k, it's defined as a number of waves in a unit distance. K equal to 2 pi over lambda with the SI unit per meter. Next, for the angular frequency with the symbol omega, defined as 2 pi f or 2 pi over t. So the SI unit is radian per second. We have the equation of the progressive wave in general, which is y in bracket s comma t equal to a sine in bracket omega t plus minus kx, where y is the distance moved by the particle from its equilibrium position, s is the distance of particle from the origin or disturbance, a is the amplitude of the wave, k is the wave number, omega is the angular frequency, positive or negative is the direction of the wave propagation. So if the wave propagates to the left, we put a positive sign here. If the wave propagates to the right, we put a negative sign here. Another alternative form to write the progressive wave equation is y in bracket s comma t equal to a sine 2 pi in bracket small t over capital T plus minus x over lambda, or we can have y in bracket s comma t equal to a sine 2 pi over lambda in bracket vt plus minus x. So next we have the comparison between particle vibrational velocity Vy and wave propagation velocity V. So in this table, the particle vibrational velocity is defined as the velocity of particles which oscillate about equilibrium position in simple harmonic motion that generates the wave. But for the wave propagation velocity with the symbol V, is the velocity at which the wave crest or other part of waveform move forward. So in order to get the formula of Vy, we will take the formula of displacement, y equal to a sine in bracket omega t plus minus kx, and we differentiate it with respect to time. So after we differentiate it, we will get Vy equal to a omega cos in bracket omega t plus minus kx. Or we can have another formula without the value of time, which is Vy equal to omega square root of a square minus y square. So for the formula of V, wave propagation velocity, the wave velocity is the distance traveled by the wave profile per unit time. So notice that a trough travels a distance of one wavelength in a time equal to one period. Therefore, the wave velocity always becomes V equal to lambda over t. T is for the period. So we have V equal to F lambda in general. So for the particle vibrational velocity, the value always varies with time. But for the wave propagation velocity, the value always is a constant. So this diagram shows the velocity of the wave moving towards the right. And here is the particle velocity. So at the turning point here, the particle has zero velocity. and the particle velocity is maximum when the displacement is at 0. And for this one, this is the undisturbed position of the string. And this is the Vy, which is particle vibrational velocity. And this indicates the direction of wave propagation velocity. From this point up to this point is called the lambda. Next, we have the displacement graph of the wave. The first graph, we have graph of displacement time, yt. And the second one is graph of displacement distance, yx. So for the yt graph, the graphs show the displacement of any one particle in the wave at any particular distance x from the origin. So we have displacement versus time. And from the graph, we can obtain two quantities. The first one is the amplitude value from here or here to the crest or trough. Second one is the period. So let's say from here to here is the value of period. For the second one, the graph of displacement distance, the graph shows the displacement of all particles in the wave at any particular time t. So we have yx graph. So from the yx graph, we can obtain firstly the amplitude here, and the second one is the wavelength. So basically this is the end part of the video. So we are going to proceed with example 1 and the next topic in the next video. Thank you for watching.